In Chapter 5, we're going to be learning all about systems of equations and inequalities. And in the first section, we're going to start by graphing a system. So this is a way to illustrate the solution to the system. And in order to do that, we're going to graph lines. And anytime that we graph lines, it's always best for us to solve for y, because when we solve for y, we're able to see the slope and the y-intercept. So we're going to be solving for y on this first equation because it is in standard form. For us to do that, let's get rid of that 2x. So let's subtract it from both sides and put it in slope-intercept form. So negative y equals negative 2x plus 1. To get y by itself, let's divide by negative 1 every single term. And that will leave us with, and since I've run out of room, I'll put it right down here. Negative y divided by negative 1 is y. Negative 2x divided by negative 1 is 2x. And 1 divided by negative 1 is negative 1. This second equation was already solved for y, so we're ready to go. So we have our first equation, and our first equation has a slope of 2 and a y-intercept at negative 1. Our second equation has a slope of negative 1 and a y-intercept at 5. So let's graph these lines. And I have my handy-dandy ruler here to make my lines nice and straight so we can get an accurate intersection, because that's what we're looking for here. So here goes, 0, negative 1. So over 0, down 1, the slope is 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, down 2, back 1. And remember, these are lines, so we're going to connect our points and put arrows on the ends because they are continuous functions. That was our first line. Here's our second line. So up to 0, 5. And then our slope is negative 1. So down 1, forward 1, down 1, forward 1. And we can see where the intersection is there. Now let's think about what that intersection represents. The intersection represents the point that both lines have in common. And that particular point is going to be a solution to this system. It will satisfy both of the equations simultaneously. It makes them both true at the same time. So that point of intersection, which is right there, is over 2, up 3. So where did the two lines intersect? They intersect at 2, 3. Therefore, we can say that 2, 3 is the solution to the system. Let's do it again, and let's do it a little more quickly this time. So next, we've got these two lines. 3x minus y equals 13. 2x minus 5y equals 0. Let's do this equation a little bit differently, because if we need to solve for y, which allows us to see the slope and the y-intercept, how about let's do this in one shot? Keeping in mind that if we were to move the y to the other side of the equation, it would become positive y. If we move the 13 from the right to the left, it becomes negative 13. So let's flip them, which will give us 3x minus 13 equals positive y. 3x minus 13 equals positive y. So that is the first equation solved for y. We just have y on the right-hand side, and that's fine. Then, for the second equation, let's solve for y by moving the 2x from the left to the right, which gives us negative 5y equals negative 2x plus 0. Now, you don't have to write the 0, but if it helps you remember that it's a y-intercept, then move it to the other side. Divide by negative 5, divide by negative 5, divide by negative 5, and we get y equals negative 2 over negative 5 is positive 2/5 x plus 0. So this is our second equation. Remember, this is a system, and a system is going to be 2 or more equations. So let's graph it. Now, this first one is at negative 13, which would be slightly off the graph. So 10, 11, 12, 13. But remember, this is only 1 point. So maybe instead of finding the y-intercept, why don't we think of this in terms of a little xy chart for just a moment? And what would we get if we plugged in a positive 1? If we plug in a positive 1 right there, we get 3 times 1 is 3, and 3 minus 13 is negative 10. That will fit on our graph. Let's plug in a 2. 3 times 2 is 6. 6 minus 13 is negative 7. Those will both fit on our graph. So let's graph those. Over 1, down 10, over 2, down 7, and we can see the slope in action here. 1, 2, 3 over 1, 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 1, 2, 3 over 1. We can graph our line now. This slope is 3, so it's got a pretty steep slope, and it is a positive slope that we can see here. So there's our first line. Let's graph our second line. It's a little bit easier to graph. It has a y-intercept at 0, and it has a slope of 2/5 up to over 5. And there's our point of intersection, up to over 5. So here's our second line. And remember, we're after the point of intersection, because where the two lines intersect is the simultaneous solution to the system. So that point right there, over 5 up to, is the solution to this system of equations. It will satisfy both of them at the same time, making them both true at the same time. Let's do it again. And this time, let's continue to move a little bit faster. This line is already solved for y. Let's graph it. The y-intercept is 4. The slope is 3 over 2. There's our point. 1, 2, 3 over 2. Down, 2, 3, back 2. So here's our first line. Remember, the more points that you plot, the more precise the graph is. Now, let's think about what's special about this equation. This equation represents a special type of line. It does not have a y. And if you recall, we made an xy chart in class similar to lines like this. X is completely restricted to being negative 2. But y has no restrictions. It could be 0. It could be negative 4. It could be 3. So if we plot these points, back 2, up 0, back 2, down 4, back to up 3, we realize that x equals negative 2 is a vertical line. A vertical line comes in the form of x equals some number. So this is a vertical line, and the vertical line has an undefined slope. Just wanted to take the opportunity to review there. And of course, the point of intersection is the solution to our system. In this case, the solution is back 2, up 1. So there is the solution. Next system of equations. Let's solve for y. Minus 2x, minus 2x, 3y equals negative 2x minus 6. Pay close attention to the signs. Divide by 3, divide by 3, divide by 3. Y equals negative 2/3 x minus 6 divided by 3 is 2. There's our first equation. Here's our second equation. It's already solved for y. So here's the first, and there's the second. Let's graph them both. So y-intercept is negative 2. The slope is down 2, forward 3. Down 2, forward 3, up 2, back 3. So using a ruler, remember the ruler is helpful to keep the graphs as precise as possible. Second line, starting at 0, 1, and slope is 3 halves. 1, 2, 3, 1, 2, 1, 2, 3, 1, 2. So it looks like now there is something special about these lines. Notice that their slopes, one is -2/3 and the other one is 3/2. If we multiply them together, we get -1. They are negative or opposite reciprocals. These lines are perpendicular, which we learned about in chapter 4. But this is a great example of the failure sometimes of solving a system by graphing, because can we actually tell where the solution is? Now we can see it and we could maybe estimate what the solution is, but in this case, even though these lines are nice and they have nice intercepts, we can't tell where they cross. It maybe looks like -1 1/3, -1.2, something like that. We're only able to estimate sometimes when we graph. So what we're going to see is another way to solve a system in the next section that will help us overcome this hurdle. So let's take a look at something else that we're going to see in this particular section. So how do we tell whether an ordered pair is a solution of the system? Well, I've already mentioned it, but a solution will make both equations true. So both equations true simultaneously. That means at the same time. So we're going to be verifying solutions down on the bottom of this page. So verify the solution. First, we'll do the one on the left, so I'll cover that up. So remember, this is our x and this is our y, and we'll be plugging in the x, y values into the equations. And we're looking to see that they are both true simultaneously. That's what we're trying to verify here by doing this problem. So first problem, the one on the left, let's plug in the x and the y. Here goes. 2 times 1 plus 3, does that equal 5? Yes, 2 plus 3 does equal 5. 5 equals 5. So yep, the equation works in the solution works in the first equation. Now we got to plug it into the second equation because it has to make them both true. So here goes. -2 times 1 plus 3. Does it equal 1? Well, -2 plus 3 is indeed 1. 1 equals 1. Yes, it checks both of them. It's verified. Let's do the one on the right. Remember, this is x, this is y. Here's where we're plugging them in. Both equations. It's got to make them both true. Is -2 plus 3 times 2 equal to 4? -2 plus 6 is equal to 4. 4 equals 4. Yes, first one checks. Try the next one. This, remember, is -x. Remember, that's -1 times x. So -1 times -2 plus 2, does that equal 2? Is 2 plus 2 equal to 2? What? Is 4 equal to 2? No. So it satisfies one, but not the other. So is -2 a solution? Not a solution. Not a solution. It does not work because it's got to make them both true at the same time.